Good afternoon, everybody. Welcome to a sunny, warm Wednesday afternoon of Chem 170 with your host, me, Dr. White. And our country's still alive after the elections yesterday. Thank God. Not to bring religion into the classroom, but thank you. Democrats didn't do as bad as they could have. They should have done a lot better. But that's another story for another class another day. All right, important information. After today's class and lab, I will send out an email with the password for test number 3. You have until tomorrow, 4 p.m., 24 hours to take test number 3 and then upload your answers as a single PDF file. Remember, this is not an open notes test, not an open internet test, not an open get help from someone else test. So please make sure you follow that. All right. And don't forget the lab you did last week is due today. I got a little behind posting lab scores. I'll catch up by Saturday or Sunday. I'll be up to date, including whatever you hand in today. All right. By the way, not Blackboard, Zoom has a new thing which I never saw working before. Either I didn't notice it or it's working now. I think it's working now, called screen sharing. And I don't have to do thumbs up, people, these fatty acids on your screen, because you see it, right? Well, I'll still do once in a while. All right, we're talking about fats and oils, and that's not what I want. This is what I want. Oops. Got to take the cap off my stylus and put it in this where I don't lose it place. And remember, all fats and oils have the structure. This is the structure. The structure of all fats and oils. It's a triglyceride triester. Here's ester 1, 2, 3. And as I showed you, oh, wait, I'm going to have you try this. Oh, either H plus or HCl, which is acid H plus, and water. What would be the 4 products you would get for that reaction? And I'll help you out. Remember, I'll do H plus, water, acid hydrolysis of an ester. You get back the alcohol plus the carboxylic acid you would have used to make that ester. So why don't you try, and what are the products for that reaction? If you're in a library, do it quietly. Or do it noisily and see if the librarian cares. I'm lucky about a couple blocks from my house, 5-minute drive, is one of the best libraries in Illinois. That's the Schaumburg Public Library. It's not as big as the downtown Chicago library, which I haven't been to in decades, but it's a really nice, well-run library. and the librarians are very helpful, and the collections are very good. And when you're done, give me a thumbs up. I see everybody's done. So if we look at ester number 1, we get R is CH2, and you get this alcohol, but it's connected to something else, and you get this carboxylic acid. Ester number 2, you get this is my R, so you get this alcohol, which is connected to CH2. Do you break carbon-carbon single bonds? No. Ooh, quick reminder. Hold on. Don't tell anybody, I'm being nice. But for today's test, remember, this is your friend. 4 bonds to carbon. Check anything you change. Make sure you have 4 bonds to carbon. And do you break carbon-carbon single bonds? No. And for those of you who've learned the method, use it. Back to our regular station reaction. And here's ester number 2 and my R prime through my carboxylic acid is R prime. We're doing it in general now. And finally, ester number 3. My R group is CH2, but it's connected to CH, OH. And my R is R double prime, so I get this carboxylic acid. Again, no new reactions. And you get this triol, 3 hydroxyl groups, is called glycerin. And these carboxylic acids, because organic chemists are lazy, instead of saying fatty carboxylic acids, we just call them fatty acids. Now, I'll talk later that this reaction goes on in your stomach. And your body, when it breaks down fats and oils, makes glycerin and fatty acids. And on Monday, I was finishing up fatty acids, and I'll never ask you what is a fatty acid, but they're long chain carboxylic acids. They're called fatty acids, and they have from 12 to 26 carbons. Now, when all the carbon-carbon, if we think of a fatty acid having this structure, carboxylic acid, where this carbonyl carbon and R are anywhere from 12 to 26 carbons, always straight, no branching. And when all the carbons in R are single bonded to other carbons, we call that a saturated fatty acid. And notice I, without thinking, used, if you worked in the industry, and I have, that's shorthand for fatty acid. And a saturated fatty acid is a carboxylic acid from fats and oils that have only carbon-carbon single bonds. And the example I asked you to learn was stearic acid. And stearic acid has this structure. And this is now the time of the semester. Well, I'll use the paren, meaning there's 16 CH2 like that right here. And then you have your carboxylic acid. So this is my R group right here in the example for stearic acid. And that you should know. If I ask on a test, draw the structure of stearic acid, you should know that. If I write this molecule and say, give me the common name, it's stearic acid. Nobody calls it octadecanoic acid, except tell students they don't call it that. Even though that is the IUPAC name, nobody uses it. All right, next, I talked about a monounsaturated fatty acid. Mono means one. Unsaturated, we learned at the beginning of the semester, meant carbon chain with either double bonds or triple bonds. Mother Nature never did triple bonds, never. Therefore, a monounsaturated fatty acid has carbon chain with at least one double bond present, carbon-carbon double bond. And the example I asked you to learn was oleic acid. And this is the structure of oleic acid. Notice it has a double bond, and this can be cis or trans. And I'll remind you in a little while what that means. If you forgot, hopefully you didn't, but if you did, I'll remind you. And similar to stearic acid, if we count this 1 plus 16 plus 1 is 18 carbons in stearic acid, oleic acid also has 18 carbons, but it has a double bond. And notice that this is carbon 1 plus 8 more carbons. This is at C9, carbon 9, and that's oleic acid. And if I ask on a test, draw the structure of oleic acid, 3 points, you should know how to do that, maybe even 4. If I give you that structure and ask what's the common name for that, or what's the name for that, meaning either IUPAC or common, it's oleic acid. I have to think for a while. That would be octadec 9-ene oleic acid. And it could be cis or trans. But nobody uses that. And that's something you should know. All right, now switches off, but you can have polyunsaturated fatty acids where you have more than one, 2 or more carbon-carbon double bonds in there. Linolenic and linoleic are examples of that, and I'm not going to ask you to learn the structure. Now, if we look at oleic acid, which is one example of an unsaturated fatty acid, here we have a double bond. And a while ago, long time ago, remember when we were talking about the alkanes double bond? When you have a double bond, and if you had a plane right here, when both hydrogens are on the same side of the plane, that's called cis. And I showed you the example. If you go back and look at the videotape, you can see I remembered, and I used this 2-butene. And when the hydrogens are on opposite side of this plane going through the double bond, we call that trans. Now, this double bond right here can be cis or trans. And let me remind you, this whole thing of the 17 carbons is the R group like I showed earlier in R or R prime or R double prime. If you think about the general structure of a fat or oil, is right here. And these R groups, when you hydrolyze this, form the fatty acids that are this R group. So what does that mean? If you have this R group from oleic acid or oleal group, that double bond can be cis or trans. And what that means is the fat or oil can be called cis or trans. How many of you have heard that medical science has told us in the last 5-10 years, maybe a little longer, that trans fats are bad for us? And cis fats are better. Still want to keep your overall fat intake low, but are better. And if you don't believe me, go to some supermarket and pick up some items, and you might see on the front, no trans fats. And they're talking about a double bond in the R group. Is it cis or trans? Now, I have a guess, but I have no idea it's correct. Why would the cis be better for you than the trans? Realistically, I really don't know. But medical science has found that correlation they feel to be true. And people feel that way. And large corporations that make food and sell food say, well, our customers feel that way, we better do that. And for a number of years now, if you go to McDonald's or Burger King, both of which I haven't been to in decades, but anyways, they do not make their French fries or other things with trans fats. It's cis fat. And it costs them extra money because you can get trans fats cheaper. Now, since I worked in this industry, I can teach you some stuff that the book doesn't have right. And that is there are different types of fats and oils. The fat that comes from beef fat is called, I should have it down here, tallow. And this you should know. And tallow, a one grade is called BFT, which is shorthand for bleachable fancy tallow. And I worked at a company on the south side of Chicago. It was an international company, but they had a plant and research there. I was the laboratory manager in charge of both quality control for the plant and the chemical research for the company in North America. And we would buy BFT, bleachable fancy tallow, to the tune of 2 to 3 million pounds a week. That's a lot. Now, another thing, which I'll write this on a separate slide, is pig's fat. And there are two types. And what I have it here, yellow grease and white grease. And pig's fat is very similar in chemical composition to tallow. And we would buy both. And the pig's fat, and even to this day, is about 2 to 3 cents, sometimes 4 cents cheaper per pound than tallow. Well, if you're buying 150 to 200 million pounds a year, 3 cents a pound difference makes a lot of money. And so whenever we could, our buyer would get yellow or white grease. And because I was part of the quality control, I would have to check to make sure whatever he was buying was good. Now, there are other types of oils, coconut oil, soybean oil, corn oil, and olive oil. Remember, an oil is a liquid at room temperature. And if you go downstairs or wherever you keep where your kitchen is, mine is downstairs, obviously, from where I am in my office upstairs in my home. And if you take up a bottle of vegetable oil or corn oil or olive oil, you'll see it's a liquid. Now, if you look at beef fat, how many of you have ever cooked either or pig's yellow grease, white grease, Have you ever cooked bacon in a frying pan? And after you take the bacon out, there's some liquid in there, which is yellow grease or white grease, pig's fat. And if you let it cool, immediately it solidifies, and that's why it's called a fat. All right, now, an interesting compound is rapeseed oil. How many of you have ever heard of rapeseed oil? Most of you probably have, and I see one of your colleagues has. Now, rapeseed oil comes from the rapeseed plant, and through most of the developing parts of the world, it's probably because it's the least expensive cooking oil, it's widely used. Well, for many years, they couldn't sell it in the United States. And one of the places they make a lot of this is our country to the north of us, Canada. And Canada, for the life of them, couldn't get the American housewife to buy rapeseed oil. So one very smart marketing executive for the that worked with the consortium that sold rapeseed oil said, let's change the name. And it's made in Canada. It's an oil, so let's call it canola oil. And if you go in any supermarket, once they changed it, people started buying it because Americans just wouldn't buy something labeled rapeseed oil. It's quite interesting. Now, time for Dr. White to get subtle. Don't you love it when I'm subtle? Hint, know this. What do I have to know? Let's find out. You should know tallow is beef fat. You should know yellow grease and white grease are two different grades of pig's fat. The others on that list you don't have to know. But if on a test I ask you what's tallow, you should know it's beef fat. Or if I ask on a test what's yellow grease or white grease, you should know that's pig's fat. Now, these chemicals are many millions of pounds per year are sold and purchased by chemical companies in the United States and the world. And so much so, since I've worked in this industry, every Friday in the Wall Street Journal, if you know where to look for it, they have the contract price. What's the price that week of tallow and of yellow grease and white grease? Because many of the contracts that companies who buy products made from these chemicals, they're based on the price they pay for that new chemical made from tallow or yellow grease or white grease is a formula based on the Wall Street Journal price of this. But you didn't know that, and that tells you how important this commodity is. Now, one thing, where do they get the tallow, white grease, and yellow grease? From when animals are slaughtered and butchered, the fat is saved and sold to companies that render it. Render it is if you take it, heat it, the fat comes out. And when the company I worked for, Unichem Chemical, year before I started, had bought the chemical division from what was then, I don't know if they're still in business, the Darling Rendering Company. And that was also located on the site where our place was, with the agreement within 5 years they'd close up the rendering plant. Do I have time? I do. And the rendering plant would get fat from meat packing companies and butchers too. Uh, Butchers would save the fat in the plastic gondolas with the garbage bags in there and sell it to Darling so they could make it into tallow or yellow grease, white grease. Now, one of the things, if at the slaughterhouse, and this Darling was located in the same area the old Chicago stockyards were, which butchered animals, cows and pigs, which is how Darling got its start. And they still got stuff from slaughterhouses. If a cow dies before it's killed, they can't use it for the meat or anything. And Darling would buy the whole cow. And now for a really strange Dr. White story. I worked at Unichema, and Darling still had their rendering plant. And it's one of the few smells in chemistry you never get used to, essentially dead carcasses. It stunk. But anyways, one winter morning, I was coming to work, and because I was a senior manager, I would go through the guard checkpoint. They had fences and a gate. The outside parking lot wasn't gated. And I had a special nice parking lot under a covered overhang. So if it snowed, or rained, I didn't have to clean off my car in the snow. My car didn't get wet in the rain, and protected it from the sun too. And I drive a little through the plant and park my car and then go to the building I worked in, which was like a 5-minute walk from where I parked. Well, one morning, and I used to start early because Unichemo was an international company, and the people there said, "Oh, you can start early because the people in Europe, when there are questions, they can call you," which was good for me because I missed traffic. I live in Schaumburg, and this was 47th and Racine, so I'd take the toll road to the Kennedy, or I would take the Eisenhower to the Dan Ryan get off at 47th, head west to Racine. Well, anyways, I'd be there about 6:30 in the morning. Here's this cold winter morning. I think it was like 10 above. And guard opens. He knew me. I waved to him. He waved back, opened the fence, the gates. I drive in, and about 20 feet in, guess what's in the middle of the road? A dead cow, frozen with its legs sticking up. So I go park, go to my office, and because I was in charge for the whole site, including Darling's rendering company that was still there for waste treatment, I knew the plant manager. I got on the phone, called him, and I said, "Bill, we got a problem." He said, "What do we do now?" I said, "Well, take a look out right by the guard tower. There's a dead cow in the middle of the road there." He said, "Oh, I'll send a forklift driver out there to get it cleaned up, taken away." And I thanked him. And that's one of my less favorite memories of the chemical industry, but that's where we got tallow from. All right, I turned the switch off, but if you had bought the book, you can see some of the saturated fatty acids, which come from saturated fats, or the R group. Oleic is 12 carbons, including the carbonyl carbon. Palmitic is 16, including the carbonyl. Stearic, you've heard about. The last one I've never worked with. Oleic, 18 with a double bond. Now here they have cis, and you can tell they're academic chemists who it can be trans too. And same thing with linoleic with 2 double bonds and linolenic with 3. You don't have to know the structures. Now, hopefully you learned for test number 3 later today, how do you name an ester? Well, the IUPAC, you drop the IC in the word acid from there, and you add AT, OATE, or ATE, and in the front, you name the alkyl group. So if we look at oleic, an ester of oleic would be oleate. drop the IC, and stearic would be stearate, drop the IC, the word acid, and add ATE. If you look at a lot of your personal care products, especially skin creams and lotions, you'll see in the ingredients the terms stearate and oleic, because products, esters made for those are made from fatty acids that come from pigs and cows. And it's nothing to be grossed out by. By the time you get it, it's been heavily purified. By the time we sold it, it was heavily purified. The oleic acid and stearic acid, that were our two main products we sold, plus glycerin, millions of pounds a week. Now, if you look at the real world and switches off for this slide, you'll see animal fats and vegetable oils. And up here you have the overall percent of saturated fats, fatty acids, which are the R group that were originally in the fats or oils. And you have unsaturated. And if you look at, let's say, beef tallow, it's about 42% unsaturated and 58% saturated. And medical science has found saturated fats are worse for you than unsaturated, or ones that are high in unsaturated or saturated fatty acids, which is why eating too much beef or lard, bacon, or even butter is bad for you. And they have human here. I don't know how accurate that is. But anyways, if you look at the vegetable oils, notice olive oil, which is, if you listen to doctors, if you're going to cook, that's the best one. I still like vegetable oil. It's less expensive and I like taste better, but I limit that greatly. But olive oil is 90% unsaturated, which is more healthy for you. All right, let's do something. First, I'll do the general reaction here, hydrolysis, which is similar to what you've already learned, but a little wrinkle to it. And this is what we use in industry to make fatty acids. Now, I've already taught you this reaction. It's acid hydrolysis of an ester. Now, what does that really mean? Well, the acid H plus is a catalyst. If I can spell it right. I tell you, I was the first one down in a spelling bee. Still probably would be. But anyways, if you don't have that H plus, the acid, this reaction hardly goes. Well, what's another way to make a reaction go quicker? And there's a rule of thumb for most, but not all reactions. For every 10 degrees increase in the reaction temperature, the reaction rate doubles. So when you heat certain reactions, most of them, they go quicker. Well, how can you do that for this reaction? Well, you use steam. And what's steam? Hot, very hot water. And you get the same products. Instead of acid catalyst, you have the increase in heat to catalyze it. And this reaction we did at Unichema, and other companies did it. And let's have you try something. And what would be the product or products for the reaction there? You took a general fat or oil and reacted it with steam. And steam, especially high temperature steam, can be very, very high temperature, hot, very hot. In fact, you have to be careful around high pressure steam because it's hot enough to kill you if you get it on you. It was, it's that dangerous to work with, but it's safer than acid and cheaper too. All right, it looks like everybody's done, so I better get to work. So if we look at this, we have 1, 2, 3 esters. Remember, when you look at a molecule, look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, to get your attention like that. And here we have an ester, steam. Here's the general reaction. So the first ester, 1, I'll get this alcohol plus this carboxylic acid. The second ester, I'll get this alcohol plus this carboxylic acid. And the third ester, I'll get this alcohol plus this carboxylic acid. And you get glycerin and the three carboxylic acids, or excuse me, fatty acids. Now, one of the things when I was teaching this for the first time, I said, I have real world experience. How can I give my students real world experience? Well, if you looked at the chart I showed you earlier, uh, tallow and yellow grease and white grease have approximately a 50-50 mixture of saturated, unsaturated fatty acids that make up the R groups. So I said, how can I give students a real world experience? And this is what I came up with. Since you can't do 50-50 on 3 esters, you can do something like this. Plus, it's my own little joke. And what's the joke? If you look at the letters on the R groups going down or up, it spells SOS, which is help, save our ship. Now, let's look at the following. This structure is the structure I will use in this class for tallow, yellow grease, which is a type of pig's fat, and white grease, which is not named after me. And if I were to ask you, give the organic product or products for the following reaction, Before I do that, let me point out one thing. Here's stearic acid. And in the fat or oil above, this is what I mean by R sub S. This is oleic acid. And this whole area here is what I mean by R sub O. Now, when I ask for on a test, like test 4, give the structure of stearic and oleic acid, I'll ask to see the actual carbons like I have here, not R sub S. But in a reaction, if this is how you're abbreviating it, then you can put R sub S for here. So let's do the following. And here's the general reaction. We have this, and I'll do this one, and I'm going to share the fun. We look at ester number 1. What's R? To become this alcohol, CH2OH. What carboxylic acid we have? Well, R prime is R sub H. So we get stearic acid, which I'll draw this way. Again, if I ask for the structure of stearic acid, don't use R sub S, but in this type of reaction, you can. Next, ester number 2, what's my R? CH2, CH, it'll be this alcohol. Notice here, R prime is now R sub O, so you get oleic acid. And ester number 3, you'll get this alcohol. Now, listen carefully. On my test, and you've seen this all semester, I ask you, give the organic product or products for the following reaction. And I would with this type of reaction. I don't ask you to balance it. So what will this give? The ester number 3 will give this alcohol, but this carboxylic acid. So you don't have to write it again because the actual products would be glycerin, stearic acid, and oleic acid. Now, for those of you who want, you can put a 2 there, or you can rewrite it. You don't have to. But in reality, this reaction just gives 3 different products: glycerin, stearic acid, and oleic acid. And you should know that this is a general structure, because we'll see more later today and also on Monday, where I ask you to learn this and use it. Mainly because I worked in this industry and you get to learn things. And this is how a mixture of oleic and stearic acid is called tallow fatty acid. Remember in quaternary ammonium salts where I used R sub T? for a quaternary ammonium salt? Well, that's a 50-50 mixture, not 50, but close to it, of this and this R groups in the of the R sub T. So if I look at it, guess what time it is? No, it's not howdy doody time. I just did a generation gap thing on you. Most of you don't even know who Howdy Doody is. But when I was a kid, he was a very popular TV show, even though I wasn't that hot on it. I liked the Lone Ranger a lot better, the real Lone Ranger. Anyways, let's take a 5-minute break, come back in 5 minutes, 1:55 by my clock, and we'll continue. I'm back. And I see all my students are back too. Hi, all my students. All right, we're talking about fats and oils and how to draw a representation of tallow, yellow grease, and white grease. And you have this triglyceride where one of the R groups is R sub S, the other is R sub O, and the other is R sub S. You could have done 2 O and 1 S, but this way I get my joke in SOS, which the students are saying, help, no. But anyways, remember, R sub S means this part of stearic acid. So when we hydrolyze this ester, you get stearic acid. R sub O is this part of oleic acid. So in ester number 2, when you hydrolyze it, acid hydrolysis, you get oleic acid. And ester 3, you'll get stearic acid again. Now, if we do the following, and says C board, so I better get to work. Wrong place, right place. Let's look at the following. What if on a test I put this? And it said, give all the organic product or products are the following. Well, what do you do? Well, tallow, how do I make a word react? No, tallow for this class is this triglyceride or triester. Everybody see that on the screen right now? And what I'm really asking in this reaction is this reaction. And here we have 1, 2, 3 esters. And hopefully you learned for today's test, you take an ester, sodium hydroxide, and water, base or saponification of an ester, you get back the alcohol you would have used to make that ester, but in the presence of base, the carboxylic acid forms the carboxylate anion or salt, either one. So if we look at this general reaction and do ester 1, R is CH2 bond to something, we'll get this alcohol. And then we'll get this carboxylate anion. It's called sodium stearate. And if you look at certain products, I won't get to it today. Monday, there'll be another Dr. White's show and tell. Don't miss Monday. And the second ester, you'll get this alcohol. And notice what's R prime? R sub O. So you'll get sodium oleate. And the third ester, you'll get this alcohol. So once again, you get glycerin, but this right here will give you sodium stearate, which we already have. If you want to put a 2 there, you can. You want to rewrite this again right here, you could. That's okay with me, but you don't have to do those. So in this reaction here, you get 3 different products. Remember, we're not balancing the equation. You get glycerin, sodium stearate, sodium oleate. And that's how you do it. And this is base or saponification of an ester. Now, this is an interesting reaction. How many of you, and I mentioned it last time, but I didn't have it written this detail, know that sodium hydroxide, the old name, is lye. And our ancestors found that they could take beef fat, tallow, in a big kettle with water and lye, boil it, and after a while, when you cool it down, you'll have a liquid in the water that's glycerin you can separate, and you'll get this white solid, which is the sodium stearate and sodium oleate, and that's bar soap. And that's why this is called saponification of an ester, because you take the triglyceride, this ester, or triester, and you make soap out of it. See all the neat things in your life you don't know about, you're learning in my class? All right, how many of you ever heard of hydrogenated fats and oils? Well, what's going on there? Well, let me ask you to do the following. Remember long ago, took a double bond, carbon-carbon double bond, reacted with hydrogen and catalyst. You break the pi bond, and each carbon of the double bond gets a hydrogen. And remember, there's a pi bond here and one sigma bond. And do you break sigma bonds, single bonds? No. Well, I'm going to give you a reaction to try. And what would be the product of this reaction? Now, I will tell you the carboxylic acid will not, under these conditions, react with hydrogen in the nickel catalyst. So it's your turn. And give me a thumbs up when you're done. And I'll give you a hint. Don't break carbon-carbon single bonds. In case you forgot, this molecule is called oleic acid. And when you're done, give me a thumbs up. Oh, everybody's done. So if we look, what's different? Well, I've got a carboxylic acid, but that won't react with hydrogen and nickel catalyst. But I do have a double bond, and that will undergo this reaction. So you break carbon-carbon single bonds? No. So I'll have CH3, CH2, 7 of them. And now this double bond, I'll break. Each carbon gets a hydrogen. And then I'll have CH2 7 times in my carboxylic acid functional group. Now, if we do a little high-level math, notice this is a CH2, right? And this is a CH2. And I've got 7 here and 7 here. So 7 plus 7 plus 1 plus 1, which is 7 plus 7 plus 2, is 14 plus 2 is 16. So I can rewrite this molecule like this. Same molecule right above. Notice right here, I have 17 plus my carbonyl carbon, 18 carbons. And this is called stearic acid. So if you hydrogenate oleic acid, you'll get stearic acid. I actually worked for a company, Unichem. When we made stearic acid, there was some oleic acid impurities in there. And to get rid of it, we hydrogenated it. In fact, I improved it, got in trouble because I, with a technician, was able to improve it. And the main research center for Unichem in where was that? Yeah, that was in Gouda, had like 100 PhD chemists and technicians. And I did something they had been trying to do for years. And the research director there wasn't happy. How come I could do it and they didn't? And he finally realized, well, this guy knows what he's doing. All right, let's try another reaction. And here's another one for you to do. If you take this molecule, react it with hydrogen nickel catalyst, what do you get? If you want to give up, give me a thumbs up. If you want to give up, or when you're done, give me a thumbs up. Remember, a carboxylic acid will not react with hydrogen nickel catalyst. Well, I see a quiet, and I'm in the library, thumbs up. All right, let's do this. What is this molecule? Well, arsabo and a carbonyl, that's oleic acid. And we saw right up here, oleic acid, hydrogen and catalyst, you get rid of the double bond, and what do you get? Stearic acid. So for the way I have this written, you could have easily done this. Oleic acid, you hydrogenate it, you get stearic acid, which I'm writing this way. You could have written it that way too, but that's that. Now for the piece de resistance, the grand finale. Let's try this reaction. Now I could here put excess. I usually don't. You put in enough hydrogen to make anything. And so you take this triglyceride, fat or oil, react it with excess hydrogen and nickel. What is or are the product or products you get? And don't forget, I have my office hour tonight if you ever need help. And after class and lab today, I will send out the password for test number 3. Boy, we're already doing test 3. Where's the semester gone? Time flies when you're having fun with organic chemistry and Dr. White. All right. So what do we do here? Well, if you look at this up above, we learned NER sub O, when you hydrogenate it, becomes R sub S. Now, will an ester react with? Will an ester react with hydrogen and catalyst? No. So, do you break carbon-carbon single bonds? No. So I'll have this ester. I'll still have this ester. But this R sub O, when you hydrogenate it, becomes R sub S. This R sub S isn't going to react. And this R sub O, just like you learned up here, R sub O becomes R sub S, sterile group, and this is what you get. Now, this is what they mean by hydrogenated fats and oils. Generally, it's oils like vegetable oil or even fats too, but usually, why do they do this? Well, it turns out something that's highly unsaturated, a lot of R sub O, double bonds, is a liquid at room temperature. Hydrogenated fats and oils are solids or semi-solids at room temperature. And why would they do that? Well, they still make it. Some of them have changed their formulation. How many of you are familiar with the product you can buy at your local supermarket called margarine? And margarine, they take inexpensive vegetable oils, corn oil example, hydrogenate it, which is not an expensive reaction to do, and make hydrogenated fats and oils, add some water, add some yellow coloring, add some flavoring, and we sell it to you as margarine, a lot more expensive than the vegetable oils we bought to do that, which means it's extremely profitable. How many of you have ever seen the product, I can't believe it's butter, margarine? And it's probably, I don't know now, but for many years it was a top margarine selling brand. And years ago when I worked for Unichema was part of Unilever, which is the huge multinational international company that owns Birdseye, Lipton Tea, and a whole lot of other companies under the Unichema umbrella ownership. Well, because I was a very high senior manager, they would have every once in a while these conferences that they brought all the senior managers to a really nice resort. And this was in Upper New York State. I think it was the Catskills, maybe not. I don't remember. It was a long time ago. And we had really nice, the place we stayed at, this resort, we had each quote unquote cabin, which was more like each one had their own suite. You had your own suite, which was a huge bedroom and bathroom. And then they fed you like if you were on a cruise ship, plus at night, all the alcohol you wanted to consume. The company paid for that. Well, the first day we had our big meeting where everybody, there was about 200-300 people there. And we're in the conference room, big like auditorium. And every once in a while, and this was before cell phones, so it's a while ago. Well, cell phones haven't been around that long, since only 20 years. Well, this was a lot longer ago. I shouldn't have said that. But anyways, the owner came in and to the whole group, he said, "Is so-and-so here? I have an important phone call for you." And this guy gets up and goes out and comes back. And about 30 minutes later or less, owner comes in and asks the same guy, "I've got an important phone call." And he goes and comes back about 5-6 minutes later, and it happens again. And finally, the senior vice president who was in charge of the whole conference said to the guy, "You've got something going on bad at your office. Why don't you just take a flight, leave right now and get back to your office, because it sounds like you're needed." And he did. And I found out later what was the problem. Well, this gentleman was in charge of the national rollout for the first time of, I can't believe it's butter or margarine. And they had made enough to cover the whole United States or sell to the whole United States. I think they had something like 300,000 cases made up. And each case, I think, had 24 in a case. And they had opened up a case before they shipped them out. And you know how it has the lid, you take it off and there's foil on top of the container? It was bulging. And if you opened up something like that and you see it should be flat and it's puffed up, there's something wrong. Well, that was the problem he had, and that was a big problem. And I don't know if this is true or not, but I'd heard through the grapevine the quick solution, because they've opened some and there was nothing dangerous or a health hazard. For some reason, something was giving off gas that was innocuous. They hired a bunch of high school students to stick hypodermic needles in to get the gas out, and they sold them. They found out it was a problem, never had it again. But think about it. The industry, food industry, takes vegetable oils, which are safe for you, hydrogenate them, and makes margarine, which is not safe for your heart, but they make a lot of money. Oh my goodness, I just looked at the clock and it's time for the lab. We gotta get going. So anyways, I'll continue on with fats and oils on Monday, but let's do today's lab. All right, everybody see polymers? I don't have to do that anymore because it just popped up on the bottom of my screen that you should see it. Is Zoom telling me the truth? Thank you. You don't know. In the past, you'd think you were seeing, students were seeing something and they didn't. But anyways, today's lab is polymers. And Dr. White's sad. Why? Because it's fun to watch students make polymers if we were face to face, but we're not. All right, so polymers are an important role in our daily life, and they come from the word poly, meaning many, mer, single units. And these are large molecules that have many repeating units, just like a large train, long train with box cars, all the same, or alternating 1 and 2. Now, the first part, if we were face to face, you would be making a polyurethane polymer. And a polyurethane is made up of an isocyanate and an alcohol, polyol. Polyol meaning more than one hydroxyl group. I just have the reaction with one. And the isocyanate usually is a diisocyanate, and I have that here. And when you do the reaction, it forms a urethane, which is this functional group, and it's exothermic, gives off a lot of heat. Now, you can put a low boiling liquid in the reaction mixture, and this way you make a foam, a urethane foam. Now, there are two types of urethane foam, rigid and flexible. If you've been in a car or if you've been in somebody's living room and you sit on a couch or your car seat, or you have some pillows that are, some of them are made from urethane foam. Those are flexible urethane foam. Now, take good notes. The rigid foam, which is an area I have patents in, is used for insulation. If you look at old refrigerators, I think I mentioned this, we went through polymers in the classroom side of this course. The old ones have very thick walls because they use a glass wall. Once they started using urethane foam as an insulator, the rigid, it's much thinner because it's a really good insulator. Now, I'll be showing you how to do this, but let me teach you something else that's important about urethane foams. Now, urethane foams, a big area is either making insulation in a plant or on a job site, a construction site, and you're dealing with people who are not chemists. And so to make it easy, the urethane foam industry To make it, they develop two sides. One is the A side, and that's where you just have the isocyanate. And then the B side, and if you go to some construction sites, you'll actually see drums labeled A side and B side on the label. This has the polyol. It has a catalyst, a tertiary amine. It has what's called a silicone surfactant. To help make the bubbles better and better insulation. And finally, it has what's called the blowing agent. And depending on the foam you're making, generally you do equal parts of A and B, you mix them together and make your foam. Now, to make it go quicker, you add more catalyst. And you can also adjust the temperature, but that's you usually can if you're at a job site, building a house or something like that. So the catalyst, putting more catalyst makes the reaction go quicker. Now, there's certain key measurements when you make a foam. When you mix the A side and the B side together and mix them up, this is a very light yellow color or even clear. This is a dark brown because for insulation, you're not worried about the color of your foam. So this is called a polymeric diisocyanate. And what you measure is called the cream time. And the cream time is when the reaction starts. And when you mix two things together, the reaction doesn't happen immediately. It matters how much catalyst. Now, why is it called the cream time? Because when you put this together in here and you start making your foam, it looks like when you pour cream into black coffee. And that's how it's got its name, cream time. Now, important thing when you're making a foam is the tack-free time. And this is when the foam is no longer sticky. And you can just touch it or touch it with a tongue depressor. And if you touch it and it's hard to pull off, it's still sticky. And as soon as you touch it and it comes off easily, you've got a measurement, the tack-free time. And in a company that makes actually board stock urethane foam, they need to know the tack-free time so when they know when they can safely take it out of the molds. And these are both important measurements. Now, one thing I should tell you right here, the cream time, that tells you when the reaction starts. And if you want a fast cream time, meaning a fast reaction, you add more catalyst. A slow cream time, meaning a slow reaction, you add less catalyst. And this reaction, you'd be making a urethane foam. What you do is it's real simple. In a plastic cup, put 10 grams, and we have a top loader balance real quick. And if you're off a little, it's okay. You put in 10 grams of the A side. In a beaker, you put in 10 grams of the B side. And then you take the B side beaker material, pour it into the plastic cup of the A side, mix it real quick, and watch. And after a while, you should see when does it turn from dark brown to light brown, which is your cream color, cream time. You feel the outside of the cup, does it heat up? And the answer is yes, it's exothermic, it's yes. And then you start testing after a minute or so, every once in a while, when it's no longer sticky. Now, this isn't the exact type, but it's similar to what you do. That's not what I wanted. Huh. All right, let's go back here for a second. Success. All right, time out
This
for commercial.
$79 headlamp.
By the way, this is a garbage product. Don't buy.
About molding foam. Specifically today, we have a 3 pound per cubic foot molding foam that we want to discuss some of its attributes. This material starts its life off as thin liquids. It's going to be mixed at a 1-to-1 volume measurement, and then it's going to expand. It's going to expand to form a very lightweight foam. And as we said, in this case, it's a 3 pound per cubic foot density foam. So it's going to expand 24 times its liquid volume to create a lightweight, non-absorbing, closed cell foam that can be easily sanded or carved to dimensional shape. It can be cast as backups or as freestanding forms. It can be painted with automotive paint and used in conjunction with fiberglass resins. In conjunction, it can be used for flotation. It has an extremely good compressive strength. This particular 3 pound foam has 40 pounds per square foot per square inch. Is going to actually be mixed and used. Right, how this liquid foam is going to actually be mixed and used. We first conditioned our liquids to 72 degrees Fahrenheit. Best temperature to be at. Hotter means faster reaction. Colder means a slower reaction is going to create higher density foam.
In real life, you don't do that.
Equal portions, liquid. In this case, we've had some pre-marked beakers. We measure out part B, and now we're going to measure out part A.
See how dark it is?
And then we're going to take a flat spatula, not a round dowel, and we're going to pour one into the other, and we're going to simply mix. And it's important that you quickly scrape the sides and the bottom of the container to incorporate all the
Yeah, got light.
so that they get fully
starting to react.
Doesn't take much. When the material starts to react, it'll form a nice even cream color, and you need to pour that into your mold. For this demonstration, we're just going to do a free rise block of foam so that you can actually see how this material expands. We'll pretty well got it mixed, and it's going to create just a little bit of heat on its own. Again, 72 degrees is the perfect temperature to start mixing that. It gives you about a minute or so of time to actually mix the foam and pour it into the mold. You got to be careful now not to put too much foam into a closed cavity mold, because it does create quite a bit of pressure on its own, and it could warp your mold. So now it's starting to come up, and actually to demonstrate this, we're just going to let it come up to kind of show you what we call free rise.
See it rising?
In this. So it comes out, it's going to expand, and within about 2 or 3 minutes, it's going to get to be full hardness. And we'll be able to actually pick this up, carve it, and show you how it's used. It's best not to get this on your hands, and I'm not wearing gloves, but you should wear gloves with this right now, because it loves to stick to human hands. That's about it. And you can see I only had about 500 milliliters of liquid, but you can get a sense of how much volume with this. Now, foam is sold in different densities, from very, very lightweight packaging foam, which is about 3/4 of a pound per cubic foot density, all the way up to heavy furniture foams, which can be as high as 15 to 20 pounds per cubic foot. And every time they go up in density, the carvability and the machinability goes up to it as well. You can see this is already forming a nice solid. And within a few more minutes, I'll be able to pick this up and actually carve it for you. Well, it's only been about 5 minutes since we initially mixed our foam. And you can see it's pretty well set. It doesn't stick to polyethylene or propylene plastics, so common garbage bags work quite well as a barrier. As you can see, it's durable and it's fairly lightweight. And as we
Now, the one he made was a low density. By adjusting the amount of blowing agent, you can change the density. Remember the one I showed the other day? That was a very high density. And for insulation, it's not that low, it's not low like what he had. Oh, by the way, when I figured out the 10 grams of each, it doesn't flow over the cup like that. And when we do it, we put newspaper down, then above that, a garbage bag, so it doesn't ruin the surface, because it sticks surface of hoods too, countertops. All right, that's a urethane foam. And you'd make that. And if you were making it, you determine the cream time, which I give you, tack-free time. Was there exotherm? And you noticed in the video, you said how it gets hot on the outside, you'd feel that. And the color is a solid and it's a light brown like what he had. Now, the next one is making nylon. And nylon is a polyamide. Now, the reaction I taught you in class was making an amide from a secondary or mean ammonia and that's how you make it. Now, when you make it in a plant or what we would do in the lab, this is slow. And sometimes you have to heat it up or do other things to catalyze it. Now, there's a derivative, something made from a carboxylic acid called an acid chloride. And this reacts just the same way as a carboxylic acid, but it's much more reactive. The rate of reaction is much faster. Now, what you lose a hydrogen here and a hydrogen chlorine, and you generate hydrochloric acid. This is an acid. And so what you normally do is put a small amount of base in there to neutralize the acid. Otherwise, the acid will react with your amine. Now, for a polymer, we use a diacid chloride, 2 of these in a molecule, and a diamine. And for this one, we'll use the diacid chloride and diamine. And I'm going to show you in a little while, but in one beaker, you put in there, and you've got to mix this up. In beaker A, we put in a solvent, dichloromethane, and then the cebutyl chloride is the acid chloride. That's beaker A. In beaker B, we put in some water, and then 5 milliliters of hexane 1,6-diamine. And in that, you also put a small amount of base. That's to neutralize the hydrochloric acid. Now, here's what you have to do if you were doing it in the lab. Here's our beaker B or A. And then what you'll do is tip A, which has the acid chloride, and then carefully you'll have beaker B, and you'll carefully pour that down the side. And what happens is after that, you'll have two layers. This is the acid chloride. And the top layer right here is the amine. And because one is in a dichloromethane, the other is in water, they don't automatically mix. And at the interface right here, they react to form nylon. And what you do is you take a hook, which is a wire, and you pull it out and you start wrapping it around a beaker. And it's fun. And again, I wish I could show you this. I thought I had a link to that. Oh, here it is. Grain freeze.
Million.
Commercial time again. I don't know why they have an atomic bomb going off at the beginning, but they do.
Okay, this is the aqueous solution. I'm going to pour this in here.
Now, here he's putting in the acid chloride.
That aqueous solution contains the acid, the diacid. And this is a solution of the hexane diamine that's dissolved in hexane, and hexane is less dense than water. So this solution is going to float on top of the other one. And then where the two solutions come together, the interface between these two solutions is where this
And you
reaction
can
is
go
going to take
back and
place.
watch this at your leisure.
What fingers do I have? Anyway, here we go.
Guys know how to put on gloves.
Gloves for another species. Here we go. Okay, so I'm very carefully going to pour this down the side, and then where the interface is, we'll have contact between the diacid and the diamino hexane.
And you would have done this in
Hexane
the
layers
lab.
floating on the top here. But of course, where they come together is where the polymer can be made, where the condensation reaction is happening. So then I'm going to reach in here,
Now
and
he uses
where the
long,
interface is, I'm going to pull out some
that
nylon.
white stuff is nylon. Now
Show you
he
what
does it
nylon
the
is.
hard way. We wrap it around a beaker
Meter.
and you can keep on pulling more and more. I've had students do that for 5 minutes. But what can we stop, Dr. White? Well, when you're tired of doing it, they keep on doing it. And that white material is nylon. Now it's still got chemicals on there, so you can't make it anything. You got to clean it up. If you were in a chemical plant, and they do. And they have extruders
Now, you
that
can see
does
you can get a
that.
lot of material out of a very small quantity. I only dissolved a few grams of the acid and the hexane diamine in here, but we get a tremendous amount of material out of here. So on a large scale, this is done not with a whole bunch of people doing this, of course, but that would certainly be a minimum wage job, wouldn't it?
And I'll let you go back and look at the video if you want to watch how long he goes on like that for another couple of minutes. Like I said, I've had students who've done that for like 5 minutes. And you would do just what I have here and do that. Now, the last reaction is a reaction of alcohols with boric acid. Actually, we use sodium borate, but it's the same reaction. And that reaction makes what's called a borate ester, which I also have a patent in. I've worked a lot in the chemical industry. If you haven't figured that out yet. Now, this is one of those rare times. Oh, he's going to balance the reaction. and it works with sodium borate, which is also commercially known as 20-multene borax. And here, if you take an alcohol, 3 of them, and react them, you'll get, oops, this borate ester. Now, if the alcohol you have has other hydroxyl groups in here, then these borate esters can be bonded to other borate esters through the R group, and you make a polymer. So today's lab, what you'll do is 2 reactions. In a dry beaker, add about 1 or 2 milliliters of the alcohol to be added and 5 milliliters of water. You mix it, then you add about 5 milliliters of, I call it the boric acid. It's really sodium borate solution, and mix it and observe. Now, the 2 alcohols is isopropanol, or I really should have 2 isopropyl alcohol, or 2-propanol, and polyvinyl alcohol, Elmer's glue. And you'll be using Elmer's glue. And Elmer's glue, in case you forgot, PVA, which I talk about when we talk about alcohols, is this structure. It's a polyol, and N is on the order of about 1 million. And when you mix the isopropyl alcohol with the boric acid solution, you get a clear liquid. When you mix it with the polyvinyl alcohol, you get a, is this scientific? A gluey, slimy, white solid, also known as monster foam.
Imagine if manufacturing automation, RCN, is
ECVU started as my college project, and
Imagine what would happen if every person in the United States suddenly visited your website. Would it crash?
hi friends,
Nope, wrong
welcome to
one.
news.
Let's try this again. There we go. See that on your screen now? Is that fun? Chemistry can be fun.
Hi everyone, today I'm so excited to show you our favorite slime recipe. This is the most amazing, softest, gooey, oozy slime, and it's so much fun to play with. First, we will begin by creating our slime activator. You use 1 cup of hot water with half a teaspoon of borax.
That's the boric
Make sure to
acid.
stir it well so that you dissolve all the powder. Once you are done mixing, you can keep it to the side. If you prefer not to use the borax activator, you could also use contact lens solution that contains boric acid. Now we'll start our slime. I'm using 1 part of glue, so 1 bottle of
We don't make that
PVA
much,
glue.
but if students want to
And I'm
make
gonna
more,
mix it
I let
with
them.
warm water. Suck it
Now,
out
I
the warm
do it a
water
little
into
differently
the
than she
glue bottle.
does. Well, you mix the water in there. We don't use a whole bottle like that. But we do have in the lab
And then
a
close
big
the top, and then
gallon
shake it.
bottle for
That
students
will
to use
help
some
spread
of.
the leftover glue inside. Then open it up and add it to your mixture. Now just go ahead and mix it all together so that you don't end up with any clumps. You want a nice smooth mixture. I tend to keep on hand a bunch of ice cream sticks because they're the easiest to clean up afterwards and they do a great job of mixing. food color of choice. I choose to use food color gel.
I have it out when we do the slab, but
You just need one drop.
and usually I tell
like to
students
do
they
it
can or
purple
cannot
color
put it in
or something
steer,
that's
whatever they'd like to
purple
do.
because we currently have a million different slimes.
For
that
this
have
slab,
two
everybody's
butter
wearing
slimes, yellow.
gloves.
We have two fluffy slimes that are pink. And you can find the recipes and video tutorials by clicking on the links. Keep mixing until you don't have any streaks left over.
Let's
You'll
jump
see
ahead.
that it starts to sticking together. As I raise my spoon, I'll show you. Yeah, see? Together in a much better way.
See how it's
Hope you're
coming
enjoying this
together.
tutorial so far. If we, and I could tell from the between 5 to 7 teaspoons. Touch the borax mix. Borax for you. Shaving cream slime. I have so many fun ideas and activities that we're going to be posting. Before this slime, my kids were currently loving shaving cream slime. It's really fluffy and so much fun to play with, but the only thing is it leaves you with a tiny, it was still a little bit too sticky. So I went ahead and added one more, mixed again, and then now you start kneading it.
And that's
The
a
more you play with it, the less sticky it's gonna get.
polyborate ester. And what she's got there is a polyborate ester. And you'll be making that in the lab. And when you use the Elmer's glue, like you just saw in the video, you get that gooey, slimy white solid. I have it formulated, just add them both together. And with the isopropyl alcohol, it doesn't. One forms a polymer, one doesn't. Hint. And for today's lab, you'd answer these questions. And let me go to number 9. How do you explain your observations with the reaction of alcohol? Notice, hint, molecular weight. And remember, the bigger, the heavier something is, the less water soluble. Oh, I just gave away the whole question. But anyways, with that, I'm done for today. Well, not really. I have my office hour later tonight if you'd like to come by and say hello to Dr. White and if you need help. Now, in about 5 or 6 minutes, I will be sending out the password for test 3. You have until tomorrow, I think 4 p.m. to have it uploaded. And unless you come to my office hour, I'll see you on Monday. By Sunday or sooner, I will send out email with the announcement that your test 3 score is in D2L. Also by Sunday, if not earlier, I will send out individual emails with your points you got for each answer on test 3. Next Monday, I will go through test number 3 answers, but I'll cut it out of video. How do you like my special effects? Snip, snip, snip. But if you can't come to the meeting next Monday, our Zoom meeting, you can come to my office hour anytime. If you can't make it to my office hours on Tuesday and Wednesday at 6 to 7:15, email me and I'll be more than happy to set up a Zoom meeting for the two of us to meet so I can go through the answers with you. With that, I'll say if you're not coming tonight to my office hour, have a nice rest of the week, nice weekend. Don't forget, I'm sending out the password in a little while. And with that, I'll say, bye, gehen gesund. I'll see you whenever. Bye.